Okay, welcome to the first video for Chapter 4. Chapter 4 basically covers the first law analysis of closed systems. So with that, we're just going to be several subtopics. Of course, we're going to look at the concept of work, boundary work. We're going to look at first law of thermodynamics as applied to a closed system and develop the general energy balance for that. We're also going to look at something called specific heat at constant volume and at constant pressure. And we're going to be able to relate those specific heats to calculations for changes of internal energy and enthalpy for gases, as well as for incompressible substances. And then we're going to also finish off the chapter with several example problems related to closed systems, the first law analyses of closed systems. So before we get anywhere, we're going to go ahead and start with the concept of mechanical work. Some of this is going to be a review from Chapter 2 because we did introduce this concept there, but of course we're going to go deeper into it in this chapter. So the concept of work, right? Work done by a constant force on a body displaced a distance s in the direction of the force is given by the following: force times distance. Now if the force is variable, we have to integrate that over the distance. So the work done by an external force acting in a direction of motion is negative, and the work done by a system against an external force acting in the opposite direction to motion is positive. Basically, the requirements for work interaction between a system and its surroundings need two things to happen. One, there must be a force acting on a boundary, and two, the boundary itself must move. So let's look at this diagram as an example. I have a piston cylinder assembly here. Inside, I have a gas at a certain pressure P. That gas will push up onto the piston, causing the piston to move against the atmosphere, right? That would be at constant pressure. So that boundary work is occurring due to the fact that this piston is moving, whether it's moving up or down, causing a volume change, an increase or decrease. The fact is that there's work being done on the boundary. Now, if you remember, with the concept of boundary work being put into terms of pressure instead of force, we have here, if you remember, let's say the integral of force over the distance, right? That's the basic definition from the prior slide. If you remember from Chapter 2, let's go ahead and take that and multiply it by 1, or area over area. I'll take the area term in the denominator, put it under force, and then I'll take the area in the numerator and multiply it by ds. What happens is that this becomes force over area, of course, is pressure, and the vertical distance the piston moves times the area of the piston is, of course, the volume. Excuse me, let me go ahead and erase that mark that appeared. So what I have is, if this is a constant pressure, if the process occurs slowly and the piston is allowed to move a small distance in a quasi-equilibrium manner, I can assume it to be a constant pressure process, and it ends up becoming P delta V. Again, that's for any constant pressure process. Now, the total work, again, done during a process, especially when the process is not constant, when the pressure is not constant, is you have to actually integrate that, right? So you have to integrate the functional form of the pressure over the volume change. Now this is, of course, we went over, is a path-dependent quantity, right? It's not a state-dependent quantity. So let's illustrate that, for example. So I have pressure here, I have a graph here, pressure on the y-axis and volume on the x-axis. Here's your first state, here's your second state, right? And I have a process path that's painted between point 1 and point 2, depending on the type of work that happens. According to this formulation, the amount of work is going to be the area under that process curve, right? And obviously for different process curves, there are going to be different areas underneath it, basically meaning different amounts of work. This next illustration shows that a little bit more. Again, here's that same pressure versus volume graph. Here's state 1, here's state 2, here's 3, A, B, and C, right? 3 different work paths that are taken, each yielding a different amount of work, showing that the work is not only state dependent, but it's also process dependent. So you need to know the final state and the initial state, and also the type of process it is, in order to quantify the amount of work that it took to make that state change occur. If I'm looking at a cycle, the net work done during a cycle is the difference between the work done by the system and the work done on the system. So let's say I have a simple cycle of two processes. I start at state 1, I go from state 1 to state 2, and then back to state 1. If I go ahead and take on a PV diagram the area encapsulated by the two process curves, it ends up being called the net work done by the cycle, where it's assumed that one process is a work out and one other process is a work in, so that the net difference between the two, the net work would be the difference between the work done of one process minus that of the other during the whole cycle. Now, we talked about the fact that work is a path-dependent quantity, so there's going to be some special cases that allow us to have formulations in order to quantify the amount of work. So let's go ahead and say, for example, we went over this before, that I'll write out the integral PDV, right? That's our functional form of work. Let's say I have a constant volume process, right? If I have a constant volume process, this change in volume is 0. Therefore, the total work ends up becoming 0 because the boundary most likely didn't move, right? So if I have a constant volume process, I don't have any work done by the system. But if I have a constant pressure process, right, this pressure is constant over the volume change, it ends up becoming P delta V. Again, that's for a constant pressure process. But there's other types of processes as well. Let's go ahead and try for an ideal gas at constant temperature, right? So how do I quantify that? How do I quantify the work done during a process that's done on an ideal gas, assuming the process to be constant temperature? Right now it seems like it's getting a little more complicated. Well, let's go ahead and try that. Ideal gas, pressure times volume equals mRT. Okay, so I'm going to go ahead, I'm going to take my ideal gas equation. I'm going to put on one side of the equation things that are changing during this process, and I'm going to put on the other side things that are constant. It just so happens that, sorry, let me rewind a little bit. What I meant to say is I'm going to go ahead and get pressure as a functional form of volume. So if I go ahead and take the ideal gas law, and I bring volume to the other side, I get pressure is equal to mRT over volume. I'm going to take that, excuse me, let me go ahead and delete. So I'm going to go ahead and take my pressure, substitute it into my work. I end up getting work is equal to the integral of mRT over volume, d volume, from state 1 to state 2. Well, temperature is constant because it's a constant temperature process. Mass is constant because we'll assume it to be a closed system. So I end up that the work done on an ideal gas during an constant temperature process is mRT natural log V2 over V1. Right, that all I did was take my work in its integral form, find the functional form of pressure, an equation for the form for pressure as a function of changing in volume. I used the ideal gas law for this, substituted it in, and I integrated. So I ended up getting the work done for an ideal gas undergoing a constant temperature process. What about a polytropic process, right? What is a polytropic process? A polytropic process is basically a process for an ideal gas where I get pressure times volume to some constant is constant, right? And so if I look at that, my work done for a polytropic process would be for n not equal to 1 or n equal to 1, I get these two functional forms of work. So my main point is that the value, the way that I quantify the work is going to depend on the process. And these are 4 different cases of 4 different processes that give me 4 different values of work. Okay, let's try a few example problems. Here's the first one. A frictionless piston cylinder device, initially at 200 liters of saturated liquid refrigerant, the frictionless piston cylinder device initially contains 200 liters of saturated liquid refrigerant. The piston is free to move, and its mass is such that it maintains a pressure of 900 kilopascals on the refrigerant. The refrigerant is now heated until its temperature rises to 70 degrees Celsius. Calculate the work done during this process. So, conveniently, the schematic is done for me. Next step, I'm going to go ahead and write down a few assumptions relative to the problem. So, excuse me, one assumption is that the pressure is constant. Another assumption is I'll assume my mass is constant since it is a closed system. So what the problem is asking me for is to calculate the work done during this process, and it is constant pressure. So if we're going to go through the steps, to find the work, right? This is a constant pressure work process, so work is equal to the pressure times change in volume for constant pressure. So I need to know the pressure, which I know is 900 kilopascals, but I need to know the change in volume. I don't know that. But I can get this in terms of properties, right? Because volume is equal to mass times specific volume. So I can change this form to be mass times pressure times delta specific volume. So what do I need to do? I need to find the specific volume of state 1 and state 2. So state 1, this is a refrigerant. I need two properties at any state to get all the other properties. Volume, specific volume, is a property. For state 1, I know that I have one property given, and that is pressure of 900 kilopascals. Do I know another property? I don't know. Let me go back and read the problem. A frictionless piston cylinder device initially contains 200 liters of saturated liquid refrigerant. Oh, it's telling me at the first state it is a saturated liquid. So since it is a saturated liquid, I know that my quality is 0 at state 1. It is a saturated state, and it is a saturated liquid. So I go to my refrigerant 134A pressure-based saturation table. Again, I go to my refrigerant 134A pressure-based saturated table because I know that it is a saturated state. So I get that my specific volume at state 1 is equal to the specific volume of saturated fluid at a saturation pressure of 900 kilopascals. So if you look that up, you should find that it's 0.000858 meters cubed per kilogram, right? Now, that's the initial specific volume. I don't know what my mass is. It doesn't give me my mass, does it? It just tells me that the initial volume is 200 liters, and that 200 liters is all saturated liquid. So I know that mass is equal to volume, and I know the volume of state 1 divided by the specific volume of state 1, right? So it's 200 liters divided by the specific volume. I may do the correct conversions, which I'm not going to do. You can do that on your own. I end up getting that I have a mass of 233 kilograms. Now, the total mass of refrigerant is not going to change throughout the whole process because it is a closed system, therefore the mass is constant, right? Now, as this thing cools, obviously as the process occurs, right? I'm sorry, it's not cooling, it's heating. As it's being heated, obviously the amount of liquid, saturated liquid, is going to decrease, right? It's going to actually go from a saturated liquid state probably to a saturated liquid mixture state. So the amount of liquid is going to be different, but the total mass all together, the whole mass inside the system of gas and refrigerant will not change because it's a closed system. All right, so state 2. I need two properties. I know the pressure at state 2 has to equal the pressure at state 1 because it is a constant pressure process, right? So state 1 to state 2 is constant pressure. And also, they tell me that the temperature at state 2 is 70 degrees Celsius. So I can go ahead, I can take those two properties and use those two properties in order to be able to figure out what state I'm in. So how do I figure out what state I'm in order to be able to look it up? Does it tell me? If I go back and read the problem statement, it just tells me that the pressure is constant and it's being heated to a pressure of 70 kilopascals. So I don't know what state it's in. So how do I figure out what state it's in? Well, if you actually go back to the pressure table, to your saturation tables. So if I go back to, again, the pressure-based saturation table, R134A, pressure-based saturation table, for a saturation pressure of 900 kilopascals, I can go ahead and look and find that at 900 kilopascals, the saturation temperature is 33.51 degrees Celsius. So the temperature at state 2 is greater than the saturation temperature. Therefore, it is a superheated vapor. So now I go to the superheated vapor tables. So you go to the superheated vapor tables. And for a pressure of 900 kilopascals and a temperature of 70 degrees Celsius, I can figure out that my specific volume at state 2 is 0.027413 kilojoules, or I'm sorry, meters cubed per kilogram. So, excuse me, this jumped ahead of me. So what I can do is I can figure out the work pretty simply now. I have my work equals mass, which I know here, 233 kilograms, times pressure, which is constant at 900 kilopascals, times the specific volume at state 2, which is 0.027413, minus the specific volume at state 1, which is 0.00858, equals 5,571 kilojoules. Right? So basically what you have is an ability to compute the work based on property changes. Okay? So that's the answer to that problem. Now, I don't want to just stop there. I actually want to use this problem as an example in doing a first law analysis for a closed system. So let's go ahead, and the problem is not asking for this, but just as practice, we're going to do a first law analysis. So let's try it. So we have in this case, this is going to be it's not in rate form. It's just going to be in total energy form. So energy in minus energy out equals the change in energy of the system. Now, if I go back and I look at what's going on during this process, this process is a heating process, right? So I have Q going in, and then I have the piston moving up. So if that's the case, if I go back to this problem and I try to quantify it, what type of energy is going in? Heat, mass, and work, right? I have no heat, energy by mass going in because it's a closed system, so the mass is constant and there's no change in mass. I have no work going into this system, but I definitely have Q going in. So I have a Q in, heat in. Coming out, do I have any heat coming out? No. Do I have any mass coming out? No. Do I have any work coming out? Yes. Work done against the atmosphere equals the change in energy of the system. Change in energy of the system is the change in internal energy plus the change in kinetic energy plus the change in potential energy. Since the system is stationary, there's no change in kinetic and potential energy, so I'm only left with the change in internal energy. So I'm left with Q in equals delta U plus work out. Next step, what type of work do I have? I have a constant pressure work. Therefore, this problem can be expanded to be delta U plus pressure times change in volume. Because it's constant pressure work. If it was not constant pressure, right, I'd have to leave the work in the integral form of the pressure. Now, what property do you remember that if you remember that enthalpy is equal to internal energy plus pressure times volume. So therefore, this is equal to delta H, where Q in equals delta H. That would be the result of my first law analysis for this problem. Now, what's interesting to keep in mind that if the pressure was not constant, the work would be left in the integral form of P dV. And delta H is not equal to delta U plus the integral of P dV for pressure not being constant, right? Now the algebra works out that if I have a constant pressure process, delta U plus P delta V is equal to delta H, but if my pressure was not constant and I had to actually find an integral form of pressure over the volume change, I would have to leave my first law analysis in the functional form Q in is equal to delta U plus the integral of P dV because the process is different than at constant pressure. Okay? That's just an illustration. We're going to go through many more example problems where we actually use and calculate first law quantities. The example of this problem was mainly just to figure out the work, but I wanted to actually use this to illustrate that the point of doing a first law analysis for a closed system.